This will be an introduction to polynomial and rational inequalities. Before I get too deep into the examples, let's start off with a general understanding of the concept. If we wanted to solve something like x squared plus 4x plus 3, which is greater than 0, how would we solve such an inequality? If this was a more basic inequality, we know how to isolate for the variable, and just remembering that if we divide or multiply by a negative number, that we have to flip the sign. But in a situation like this, where we have higher powers for x, situations that were complicated when we solve regular equations, we have a little bit of extra complexity when solving an inequality. What's really going on is a combination of graphing and our basic understanding of solving equations. So let's actually look at this same polynomial and look at it as a polynomial. If I looked at this, well, we know this is a quadratic. The positive x squared tells me about its end behavior. If I factor, I could end up figuring out that both -1 and -3 would be the zeros. So -1 comma 0 and -3 comma 0 would be the x-intercepts. And if I also did a little bit of y-intercept work, I'd find a y-intercept up here at 3. I know I start up here. I'd be passing through, looping back, passing through. And that would be the graph of my polynomial. So if I wanted to know where is this greater than 0, it's the same thing as looking at this graph and looking for the regions where the graph is above the x-axis. That the x-axis represents the equation y equals 0. So if I want where this is greater than 0, look where it is above the x-axis. This is still a where question, so I'll answer by x's, and it's not an individual x. This is above the x-axis for all of these x's. This is above the x-axis for all of these x's. So this inequality would have solution -∞ to -3, union -1 to +∞, representing this interval and this interval. If this was a greater than or equal to, well, then we would just include these endpoints. If we wanted x squared plus 4x plus 3 is less than 0, well, now we want the region where this is below the x-axis. So I would just be looking at this little section, and I would just get this smaller interval. There's nothing that tells us that greater than 0 leads to 2 intervals and less than is 1, or greater than gets the infinities, less than is not. That's just what happened in this particular example. So if we can look at a graph of the polynomial or the rational inequality, we could answer the inequalities by just looking where we're above or below the x-axis. But now let's take that exact same example and let's solve it without drawing the graph. That's what we really want to get used to. This is the full understanding of what's happening, but when we actually get to, practically speaking, the technical aspect of solving these, we're going to get a separate technique, but it's based off what's happening here. That we're looking for where the graph is above or below the x-axis, and in order for us to know that, we have to first establish where we touch the x-axis. So if we're going to solve an inequality, let's treat this like it's a brand new fresh problem. Solve x squared plus 4x plus 3 greater than 0. Well, the first thing to realize is that we're lucky that this is already in terms of 0. There are some examples in your book and in the notes that I give where that is not the case, and that's the first thing we would do. But once we get it in terms of 0, then we'll treat it like it's an equality, and we'll solve this equality to get these important points. So to solve this, I'd have to factor. I'd set each of these equal to 0 to get these two solutions. I'm not looking for the x-intercepts here. That's technically what they are in the picture, but I don't have to make them xy pairs. What I'm going to do is I'm going to take my x-axis and put those important x values in numerical order. The scale is not important here, just that they are in order. And now what we will do, These are the x values, and since we had two of them, our x-axis is now broken into 3 separate intervals. And now what I will do, I will take a test value, an x value from each of these intervals. I will plug it back into the polynomial to determine the sign. When I plug in, I always prefer the factored version. That will simplify our work. But that's what I'm doing. I'm looking at each of these intervals. An interval that goes from negative infinity to negative 3. Pick an x value from that interval. I will pick negative 4. I think it's very important to keep these values separate from these values. These are the values that are going to set up our intervals, but these are the values we're using to test the signs. I will take that. I will plug it into each factored piece. Negative 4 plus 3 is negative 1, so negative. Negative 4 plus 1 is negative 3, so negative. I don't care about the numbers, I just care about the signs, because any negative number times any negative number will give me a positive. And I like to put my resultant sign, my final sign, on top of my interval. Notice, I use negative 4, but the x I pick doesn't matter. If I picked x as negative 10, I would have got negative 7 times negative 9. So the number I would have gotten is different, but I still would have gotten a negative, and you multiply two negatives and you get a positive. So let's keep doing that. Now I need a number between negative 3 and negative 1. So I'll pick negative 2. I'll plug that in. Negative 2 plus 3 is positive 1, so positive. Negative 2 plus 1 is negative 1, so negative. And any positive times any negative gives me a negative. One more interval. Some number bigger than negative 1, I'll use 0. 0 plus 3 is positive, 0 plus 1 is positive, and any positive times any positive is a positive. Now I'll come back to the beginning. We initially had this greater than 0 and changed it to equal to 0. Now the greater than comes into play. The fact that we wanted greater than means we wanted the positive intervals, the intervals where the function was positive. And that's what we're getting here. These two positive signs are representing two intervals, specifically these two intervals where the function is positive, and that matches the answer we had when we looked at the graph. If this was a less than, then I would have wanted the negative interval, and that interval coincides to what we saw from our graph. So again, a nice technique, first treating it like it's equal to 0 to get this set up, and then using x values to test each interval. What is most common in your final resultant line is that the signs switch, but we cannot assume that is what happens. We actually have to test. Let's do another example. In this one, let's look at a rational function instead of a polynomial. Let's solve x cubed plus 2x squared divided by x squared minus 16, and let's do where this is greater than 0. Once again, nice that this is already in terms of 0. There are a couple examples in my notes and in the book. You have to move pieces to the other side. You have to get a common denominator. But once we get this one fraction, we're going to do essentially the same thing, except instead of just setting it equal to 0, we're going to set both the top and the bottom equal to 0 to get all of our important x values. So when I set the top equal to 0, and x squared would factor out, x plus 2 left behind, x squared equals 0 would give me a 0, x plus 2 equals 0 would give me x is negative 2. Then I'll do the same thing with the denominator. X squared minus 16 equals 0. Well, that's the difference of squares. So we get x is negative 4 and x is positive 4. It really doesn't matter that these x's came from the numerator and these x's came from the denominator. These are all the important x values that we have. Some people like, especially because now we had a fraction, let's go back and rewrite that fraction in its factored form. but we still care about where it is greater than 0. We're going to set up our test intervals. Now I have 4 x values that I have to use to set up my intervals, and I'm still going to test each one and look where we get the positive signs. So, putting these in order, -4 would be the most left, then -2, then 0, then 4. Once again, notice I'm not trying to do this to scale. -2 is 2 units away from 0, 4 is 4 units away from 0, but I just need to make sure these are in order. And now we had 4 important x values, so we have 5 intervals left behind. -infinity to -4, -4 to -2, -2 to 0, 0 to 4, 4 to infinity. We're going to pick an x value for each one, test the signs. And that's why, once again, I like to put the factored version together. I'm going to take each of these test values that we get, plug them in here, and just record the signs similar to what I did here. Here we were multiplying, but whether we're multiplying or dividing, 2 negatives make a positive, and a negative and a positive stays negative. So let's do that with this next example. So I'm going to start off with x equals -5. There's a lot of bookkeeping in this section. Some people like to write out every factor. They make these whole big charts, but this is the essence. Getting the important x values and getting the final sign is what we need to be able to do. If you don't want to write this out, or you can keep track of the signs in your head, that's fine, but just realize there's a lot of sign work here. It's easy to forget a plus or a minus. So starting with -5. -5 squared is positive 25, but really positive is what I care about. -5 plus 2 is -3, so negative. Divided by -5 minus 4 is -9, negative. -5 plus 4 is -1, negative. And again, multiplying or dividing, it doesn't matter. A positive times a negative is a negative divided by a negative is a positive, that positive divided by a negative. Basically, these 3 negative signs leave me with a resultant sign of a negative. Keep going, all the intervals. It's nice when we have whole number values we can use, but this little shortcut I'm showing you with the factored version, even if these were fractions, even if I pick something like x is -2.1, I could still do the sign work. -2.1 squared is positive. -2.1 plus 2 is negative. I could still do that, but certainly it's easier to use a whole number if I can. I want to make sure I keep my intervals separate, so I'm just lowering this just to be clear. This went with this interval, this goes with this interval. But I'm plugging in here. -3 squared is a positive, -3 plus 2 is a negative, -3 minus 4 is a negative, but -3 plus 4 is a positive. 2 negative signs gives me a result of a positive. As we said earlier, not uncommon at all, very common actually, that the sign switches from one interval to the next, but I can't just assume the next is negative, then the next is positive. I need to do the work. Just because that's the common thing that happens doesn't mean it always happens. So let's keep going. Next, I'll use x is -1 for a value between -2 and 0. -1 squared is positive. -1 plus 2 is positive. -1 minus 4 is negative. -1 plus 4 is positive. One negative sign gives me a negative. And now I'll go to x is +1. 1 squared is positive. 1 plus 2 is positive. 1 minus 4 is negative. 1 plus 4 is positive. We still get a negative. And this is what I was saying earlier. So common, negative, positive to negative, but we didn't flip to positive. And that's just what happened with the signs. So we have to make sure we test each interval. I still have one more interval left, and then I could finish this problem. I'll use x is +5 out here. 5 squared is positive. 5 plus 2 is positive. 5 minus 4 is positive. 5 plus 4 is positive for a positive result. We can now put our answer together. I wanted where this was greater than 0, so I wanted the intervals where it was positive. I got 2 of them. This interval is -4 to -2, and then this interval would be 4 to infinity. If we wanted where this function was less than 0, then we would have wanted the negatives, negative infinity to -4, -2 to 0, 0 to 4. We wouldn't include the 0. It's easy to just say we go -2 to 4, but technically something happened at 0, and without having the equal to part, we should keep these as separate intervals. But this one wanted greater than 0, so we wanted the positives, and that was our answer.